So the next thing I want to do, now that we've established the two formulas for the sum of the difference in the cosine, is to use those formulas to calculate some trig values that we don't already know, to get exact values, not just using a calculator, punching it in and getting decimals, but I'm talking like exact values with roots or whatever we need, cube roots, square roots, stuff like that. So just like we did with the 30, 45, and 60 degree angles, where we have, you know, your square root of 2 over 2, or your square root of 3 over 2, or your 1/2, those different values, we can have similar exact values for other angles like 15 degrees, and now we can use these formulas to calculate those, okay? Because 15 degrees is really a combination of other angles that we already know now, all right? So a couple things that are going to be helpful though in doing these problems is just to keep a note of your two special triangles. I like to write these down just so I don't forget, because that, you know, in case you don't have these memorized, you know, your sine cosine values for the special triangles for your 30, 45, and 60 degree angles. So I'll write down the special triangles just to keep them as a reference as we need them, and then we can always refer back to them. So first of all, your 45, 45, 90. Right, 45, 45, and we know the side lengths are 1, 1, square root 2. So you should have those memorized or be able to find them quickly. And then of course your 30, 60, 90 triangle. We've used these tons of times already, so that's 1, 2, and root 3, and that's 60 degree, and that's 30 degree. And also, of course, you know, your radian measures 45 is pi over 4, 60 is pi over 3, 30 is pi over 6, okay? So just keep those in mind, and we'll refer back to those. So first of all, cosine of 15. Well, 15 degrees can be written as the difference of two of these angles that we know. If you look at these angles, you could think of it as, I don't know, 60 minus 45, for instance. Or you could do 45 minus 30. Either one, you get 15 degrees. I'll do 60 minus 45 just for this example, but again, it doesn't really matter which you choose, you get the same answer. So I'm going to write this cosine 15 as the cosine of 60 degrees minus 45 degrees. Again, 60 minus 45 equals 15, and so these are equivalent to each other. And now I have a subtraction with two angles that I know. So we're going to apply the difference identity here for the cosine, and that would be the cosine of the first angle. So I'll use AB, that's going to be the first angle, second angle, first angle, second angle. Okay, so it doesn't matter, it's arbitrary. Well, it does actually because of the minus. I guess well, the way it plays out, it doesn't really matter. But I've got a 60 and a 45, so I'll just use A is 60 and B is 45. So we would have the cosine of A, which is 60, times the cosine of B, which is 45, plus the sine of A, which is 60, times the sine of B, which is 45, okay? So this cosine of 15 is equivalent to this expanded form with the 60s and the 45s, using that formula. Then I can calculate each of these individually using my special triangle over here with the 60s and the 45s. So cosine of 60, adjacent over hypotenuse, that's 1/2. Cosine of 45 degrees, adjacent over hypotenuse is 1 over root 2, or, you know, when we rationalize 1 over root 2, we know that it's root 2 over 2, so I'm going to write that one in the rationalized form. Rationalizing the denominators is going to be very helpful in this particular, with this particular material, because we're going to be doing stuff with these fractions now. And if I had 1 over root 2 here, when I start to combine these things, it's going to be very hard to add and subtract denominators or fractions whose denominators have roots, because then you've got to get LCDs, and the roots just make it more difficult. So it's going to be easier to have the roots on top than on the bottom. The sine of 60, sine is opposite over hypotenuse. It's root 3 over 2. And then the sine of 45 is your 1 over root 2 again, or root 2 over 2 when rationalized. Okay? And so now I would combine these, multiply these two, and then multiply these two, and then add with the common denominator after that. Okay? So 1 times root 2 is root 2. 2 times 2 is 4. Right? So root 2 over 4 plus root 3 times root 2. You can multiply the two numbers under the roots. It's root 6. And then 2 times 2 on the bottom is 4 also. And then I can add these two terms because they do have a common denominator of 4. However, with addition, you cannot combine the radicals, or you could think of them as unlike terms if their radicand, the stuff under the radical, is different. Okay? And so here I need to keep them separate. It's square root of 2 plus square root of 6 all over 4. As a single fraction. Okay? Now that doesn't look real nice, but it is. It's not too bad. Root 2 plus root 6 all over 4 is the exact form of the cosine of 15. Okay? So it's exact value. Okay? So if you're asked for the exact value, you want this. It's the most simplified form that involves no rounding or decimals in any way. All right. Now, I can verify to you that this works by using the calculator and getting the decimals and just showing you that it all works out well. Okay, so I'll use the calculator and make sure I'm in degree mode, which I'm not. Let's get it in there. Okay, I'm in degree mode now. And I'm going to type in cosine of 15 degrees, and you'll see right there it's about 0.9659, whatever. Okay, so that value is approximately 0.9, what did I say, 66, if I round that off. Okay, now I'll type this in and just show you that the decimal will be the same. Okay, to type that in, I'm going to put parentheses around the top. Parentheses square root 2. I'll show you in a moment here what I actually typed in. Plus root 6. Divide by 4. And you can see that that shows up to be the same, 0.966 roughly. Okay? Alright, so anyway, that's just to verify. So this thing also approximately equals 0.966. Again, I wouldn't be looking for that decimal value. I'd be looking for this exact value. I just wanted you to see that the decimal forms do match up. Okay? Okay. So anyway, it works out kind of nice. I like that. And that's using the difference identity, right? And again, I mentioned at the beginning, we could have used 45 minus 30 instead of 60 minus 45. You would get the exact same thing. Now you'd have 45, 30, 45, 30. You may end up having some of these switched around, but when you combine them at the end, you might have root 6 plus root 2 over 4 or something. But it's the same value, right? And so it won't really change anything. Let's try another one. This one's kind of interesting. Let's get rid of this. The next one I'm going to run through is the cosine of 5 pi over 12 radians. All right, this one's in radians now. The tricky thing with radians is trying to figure out what it's the difference or sum of. If I were to think of these as in radian form, the 45 is pi over 4, the 60 is pi over 3, and the 30 is pi over 6, that could help to figure this out. And 90, of course, is pi over 2. Maybe that'll be helpful. what I want to do is combine those in some way to get 5 pi over 12. Well, that's not always obvious, right, without trial and error. And that could take a while if we do trial and error. What I would tend to do is I would try to split this up into two fractions that reduce nicely. Obviously 12 isn't any of our denominators over here, but maybe if we use something like a 3 over 12 or a 4 over 12 or a 2 over 12, something that will reduce to make one of these fractions, then that might be helpful, okay? So I look at 5 pi over 12 and I think, well, what can I add up to get 5? Well, I could do 1 pi over 12 and 4 pi over 12, or 2 and 3, right? Those are really the only options. Well, 1 and 4, 1 pi over 12 doesn't really help us out. 4 pi over 12 would, but if 1 doesn't work, then 4 isn't going to be that helpful either. Let's try the 2 and the 3, because I know that both 2 and 3 will reduce with the 12. So I'm going to try that. Okay, so think about it this way. 5 twelfths is the same as 2 twelfths plus 3 twelfths. Right? 5 is 2 plus 3. I'll stick the pi's in there. So now I've got 2 pi over 12 and 3 pi over 12. Each of those reduces. Right? So I've got cosine of, well, 2 over 12 is 1/6. 3 over 12 is 1/4. So I get pi over 6, pi over 4. That's useful. Pi over 6 is a 30-degree angle. Maybe I'll write that a little bigger. There's 30-degree, and pi over 4 is 45 degrees. Right? So now I can utilize my special triangles, and I have a sum of two angles now. Okay? So we were able to break this down, 5 pi over 12, into two fractions that reduced nicely into some of the ones that we have over here, some of the angles on our special triangles. Okay. Ultimately, we really want to break it down into these three angles, or maybe pi over 2 could also be helpful. That way we can combine, add, and subtract, and use those formulas. So here I've got a sum. So I'm going to write out my sum formula. Remember, the sum becomes a difference. So we're going to have the cosine of the first angle times the cosine of the second angle minus the sine of the first angle times the sine of the second angle. Okay, so that's the formula then for the cosine of a sum. Then we calculate each of these using our special triangles. Cosine of pi over 6. Cosine is adjacent over hypotenuse, so that's root 3 over 2. Cosine of pi over 4, 1 over root 2, or we could write it as root 2 over 2. Then we've got sine of pi over 6. The sine is opposite over hypotenuse, so that's 1 over 2. And the sine of pi over 4 is 1 over root 2, or we could write it as root 2 over 2. And then again, we can multiply, multiply, and finally subtract. So this would be root 6 over 4 minus root 2 over 4. And when I combine those, I cannot combine the two terms on top because they're unlike terms with the different roots. So it's root 6 minus root 2 all over 4. Right? Again, I could verify this on the calculator by typing in cosine of 5 pi over 12, so that make sure it's in radian mode, and then type this guy in, and your decimals should be the same. So I could run through that and just verify it very quickly, change my mode to radian, and I type in cosine of 5 pi over 12. And you should see right there, hopefully that focuses. Get that focused. Not focusing. Alright, well, anyway, hopefully you can see it blurry. It's not focusing. 0.2588 is the decimal. that. And then the other one, if I were to type in parenthesis root 6 minus root 2 parenthesis divided by 4, you should see exactly the same decimal pop up, 0.2588. Okay, so that just verifies it for you. This guy here, same thing. All right, so kind of neat how these formulas work out, and they now allow us to find exact values for angles that we haven't already seen. 5 pi over 12 ends up being a 75-degree angle, obviously, because it's 30 and 45. So, so now we've got a 15-degree angle, 75-degree angle, and we can mix and match some of these things in order to get some other interesting angles that we haven't already seen. Okay. In the next video we'll talk about how to further use these two formulas.